But we can also have a simpler all-pass filter that will have one pole and one zero in the z-domain for the transfer function. So this is the transfer function of an all-pass filter with one pole and one zero, where a is a complex number and a superscript with specifies the a bar specifies the conjugate complex number, and we observe here that we have a 0 at z equals to 1 divided by a, and a pole at 0 equals to a. So the pole and the 0 are at conjugate reverse locations. So it's easier to visualize this if we have an example, and we can use Python. So here we will set a equals to 0.5, and we want to obtain pole 0 plot. So here we are defining a function to plot poles and zeros. So it will display a nice plot like this. And here we will have our a and our b, the arguments of this function. So we have a is equal to a and b is equal to 1 divided by a conjugate. A is equals to 0.5, and then when we plot, we see here a pole at 0.5 and a 0 at 2. So we have a pole at 0.5 and a 0 at 1 divided by 0.5. That's 2, and this is what we have here. So this is a function. Most of the function here is doing to shift this axis and then plot this unit circle, and then we also have here we're plotting real part, imaginary part of a, real part, imaginary part of b, and where this results into this plot here. So how can we see that the magnitude of the frequency response is equal to 1? So how can we see that indeed this is an all-pass filter, that the magnitude of this transfer function is 1? So if we rewrite the frequency response, replacing z by e to the power of j omega, we will see now this 1 here before the exponential as magnitude 1. We have here that the numerator is the conjugate complex of the denominator, so the magnitude cancels to 1, and overall the entire expression has a magnitude of 1. So the magnitude of this is equal to 1. So we can see that using just one pole and one zero, we can obtain a magnitude of constant 1, and this is what we want for our all-pass filter. But more interesting now is the resulting phase, and this phase function can be found in the book of Oppenheim, the discrete time signal processing, and is given by this equation here, where r is the magnitude of a and theta is the phase angle of a. So a equals to r times e to the power of j theta. So observe that so far we assume the phase to be linearly dependent on the frequency. So for it was minus capital omega times d, and here we see to be quite non-linear with these trigonometric functions. So we can plot this resulting phase over the normalized frequency, and we can compare it with the phase of a delay of one sample, for example, where we will get this linear phase minus capital omega. And so let's do this example. If we will plot for a equals to 0.5 and a equals to minus 0.5.